Good afternoon, everybody. We have discussed about streamline flow or steady flow. We know that a liquid flows steadily if its speed is of a particular value, and that particular value of velocity we called as critical velocity. So, depending on the critical velocity, the fluid motion can be streamline or turbulent. This critical velocity, we have seen that it depends on the density of the fluid, diameter of the pipe, and the coefficient of viscosity. Now we have a particular number showing the nature of flow of liquid through a pipe. So if we consider a pipe of diameter capital D through which a liquid of density rho and the coefficient of viscosity eta is flowing with a velocity v, then there comes a number, Reynold number, which is equal to rho v d by eta. This number for that particular liquid decides whether the flow is streamline or turbulent. For almost all the liquids, this Reynold number, which is from 0 up to some 2000, it comes within the range like that. If this number is below 1000, the flow will be steady, that is a streamline flow. But if it is greater than 2000 or above that, then that's a turbulent flow. In between, that is from 1000 to 2000, we can say it's unstable. It can change from turbulent to laminar, or that is streamline, or from streamline to turbulent. So this number decides how the flow is. Okay, now let us discuss about the force between molecules of a fluid. The figure shows the intermolecular force versus distance of separation between the molecules. So the force between the molecules of a substance we can call as intermolecular force. This intermolecular force can be attractive or repulsive. So every substance molecules maintain a particular distance. It is of the order of Armstrong, that is 10 power minus 10 meter. Suppose if the distance between molecules is more than some 10 Armstrong, then these intermolecular forces are very small. For example, gas molecules, if we take, the separation between each molecule will be greater than 10 Armstrong. So the force between them will be very weak. But within some 5 Armstrong to 10 Armstrong, the force will be considerably more attractive. But if the separation is very low, like very small separation, if it is like less than 3.5 Armstrong and all, the molecules try to face a repulsive force. In very short, if I say molecules, when you bring the molecules too close, they feel a repulsion and they keep a particular distance. When the separation is increasing, they try to be attractive and come closer. That's a behavior. So that's a graph showing. So the force of repulsion increases if the separation is less than 3.5 Armstrong. So this R is the separation between the molecules. Force of repulsion of R will be high if the separation is less than 3.5 Armstrong. From 3.5 up to some 5 Armstrong and all, the force will be attractive and little bit attractive. This attractive force increases up to some 5 Armstrong, but beyond 5 to 10 it is decreasing and it goes. That's how the intermolecular force between the molecules act. There are two types of intermolecular forces. One is called adhesion, other one is called cohesion. Consider the molecules present in the substance. We can consider a particular substance, for example water. There are intermolecular forces. Those intermolecular forces are between same type of molecules, for example water molecule and water molecule. That kind of force, when the force is between same kind of molecules, that is called cohesion, force of cohesion. But if we consider water taken in a glass container, the intermolecular force is between water molecules and the glass molecules. So the force is between different kind of molecules. We call it as force of adhesion. So while you're writing with your pen on a paper, the force between molecule is force of adhesion. If you put a drop of water on a lotus leaf, the water drop will be of a spherical shape. It is because the cohesion is more there. The force between water molecule is more there. We'll discuss that part later. For time being, understand what is adhesion and what is cohesion. Force between same kind of molecule is cohesion. Force between different kind of molecule is adhesion. There is a particular distance with which a molecule can exert a force of attraction on another molecule. This range of distance we call as a molecular range. Similarly, another one term is sphere of influence. So this molecular range of a molecule you consider, suppose you consider one water molecule surrounded by many other water molecules. This water molecule at the center can exert force on nearby molecules. If we draw a line, or if you connect all the molecules over which this water molecule can apply a force, it becomes like a sphere, and this sphere is called a sphere of influence. Now let's consider a container in which a liquid is taken. For example, let it be water. So here if I consider a water molecule, this water molecule can exert a force on a water molecule here. It can be able to apply here, it can be able to apply a force here, here also it may be able to apply. So if I join all these molecules, I get a sphere. This is the sphere of influence. You consider the topmost layer of water. These molecules molecular range is marked here. Here the sphere of influence cannot be drawn because this sphere is incomplete here, this side. Here all there are no molecules, so only the lower half of this sphere is present. and this layer is called surface film. Surface film means the topmost layer with the thickness of molecular range. This is the thickness of that. This layer is called surface film. This liquid surface has a property. This surface, if you consider the molecules here on the surface, all these molecules are under the influence of other molecules which are below this. So if I consider one molecule here that is under the influence of this molecule, this will be pulled down. This will be pulled here. This will be pulled here. But if we consider this molecule, this is pulled in all direction. There is an attractive force by all the nearby molecule. So there is no net there is no resultant force acting on it. But the topmost layer of the liquid, if we consider, all the molecules are under a particular force which we call a tension. And the tension is called surface tension. So the free surface of the liquid at rest feels a tension, a pull downward. That tension is called surface tension. So as a result, what happens is the area of the free surface will be minimized. It will be very lesser because of the pull downward. How this mathematically measured is, if F stands for the force, this surface force, if you mark as F, and if this layer has a length L, length of the layer if it is L, then this force acting per unit length, if we consider unit length, maybe 1 millimeter or 1 centimeter unit length, if we consider, or even 1 meter standard, let's go, then 1 per meter, the force acting per meter. This is actually an imaginary line and all. Here this is actually imaginary. So that force per unit length is called is how we can measure surface tension. So if you make an equation for surface tension, it will come to force per unit length, which I can mark as F by L. It has a unit in Newton per meter. It's a scalar quantity, no dimension for that. Sorry, no direction for that. And its dimensional formula will be m L to the power 0 T to the power minus 2. Force by length. Force is mass L T to the power minus 2 divided by dimension of length is L. So L cancel. That's how it comes 0. So this surface tension we can define as the force acting on unit length of an imaginary line drawn tangentially on the surface of the liquid at rest. So on the top surface of this liquid, we can draw an imaginary line tangentially to the surface. That line we can draw, then the force per unit length is our surface tension. So if you want to increase the area of this liquid, what you need to do is you have to do some work, because these molecules are under a force. So if you want to overcome that force, and if you want to increase the area of this surface, you need to do an external work, and that external work done will be stored as the energy of the liquid surface. So the liquid surface has energy. That energy is called surface energy. So it is defined as the work done against the force of surface tension to increase the area by unit amount. So if there is a attractive force, as there is a force acting on the liquid surface, if you want to increase the area of the liquid, you have to do an external work. That work is stored as the energy, that is surface energy. So let's see how that surface energy can be calculated. So for that, what we can do is we can consider a rectangular metallic frame. So here is a metallic frame, a frame made of metal, any metal you can take. and that is ABCD, this frame, whose three sides are closed but one side, this PQ. This is another small wire like structure. This is free to move, this PQ. This wire alone is free to move, but this ABCD is fixed. If you dip this frame completely in soap water, suppose you put it in soap water, take it out, you can get a soap layer here, this soap layer. We all know that this soap layer, if you make like that, this PQ, if this is free to move, this will come this side, it will move towards the left side. That is because of the surface tension given by the soap layer, and that surface tension is marked as S. Now what you need to do is, you can apply an external force F. From outside you can pull this PQ towards the right side a little bit, maybe by X centimeter you can move. So you are applying a force against the surface tension. So when you apply the force and if you move this PQ, you have made a displacement here, you have done a work, external work is done. This work done will be the surface energy, because as per work energy theorem, whenever work is done, that is converted as the energy. So this work done in moving this soap layer by a little bit, by x distance, is what our surface energy. Now suppose if S stands for the surface tension of the soap solution, we can, as per the definition of surface tension, we can write surface tension is force by unit length. F by L we have taken in the previous case, generally F by L. F by L means we have taken a liquid in a container, its top surface alone we have considered. That is why we have taken F by L. But if you take a soap solution taken in a frame, that frame has two sides. On either side of this we have a soap layer. We have soap layer on either side of the frame. So because of this two sides, we have a term here, F by 2L. There may be a confusion why we have taken like that. Look at this picture. This is water in a container. Here only top surface has a layer. Only that surface has a liquid a surface tension. But if we take the metallic frame, there comes, if we take this metallic frame, this side we have a surface, on the other side also we have a surface which is under tension. Here in the previous one only one top surface is under tension, but here both sides are under tension. That's why this S is F by 2L in this case. So from that we can write F is equal to S into 2L, surface tension into 2L length. Now as we told, you do work against this, you apply force and move this layer by a distance x. The work done is force into displacement F into x. F is S into 2L into x. This L into x we know, that is the length into displacement. L is the length of this wire, x is this movement, distance moved. So L into x is the area. Other side also, back side also, there is a movement for this layer. So 2Lx is the increase in the area. That's what delta A. So look at the equation, S into 2L into x. This 2Lx is delta A, which is the increase in the area. So work done, we got it as surface tension into increase in area. So surface tension is work done divided by delta A, work done by increase in area. So this work done is actually the surface energy. So the surface energy is S into surface tension into increase in the area. So the two terms, surface tension and surface energy. Now let us consider the pressure on liquid surface. Let's consider the pressure on liquid surface. We told on the liquid surface is like an elastic membrane, like it's always under a tension. So it's like a stretched elastic membrane. So if we consider a plane surface, if the surface or top surface of the liquid is plane, then this molecule will have a force acting on all direction from all the topmost molecules. So net pressure on that molecule will be zero almost. But if we consider this kind of liquid surface, you might have seen this kind of liquid surface, maybe water taken in a glass will be like this concave shape. But if you have ever seen mercury taken in a glass tube, this will be convex shape. The topmost layer of the liquid will be convex in nature. So let's come to this general case where almost all the cases the top surface is a concave surface. There the resultant force here, all as there are more number of molecules, suppose you consider this molecule at the center, this will be under the force of a molecule here, it will pull it towards this side, this molecule will pull this towards this side, so there is always a greater force towards the upward direction. That's why this concave shape happens. So the pressure is zero in the first case, there is no extra pressure because no excess pressure because the forces got balanced. But here there is the force are not balanced, there is an extra pressure towards the upward direction. Same way this molecule here will be pulled down by a molecule here. Suppose here is a molecule, this molecule will pull it towards this side downward, so there is also an excess pressure. Here it is a downward, here it is upward. So we will calculate how we can measure this excess pressure. That's what our next task. Another important term which is very useful here is angle of contact. As I already told, suppose you take water in a container, like this water in a glass container you take, the topmost layer will be a concave shape. You consider a tangent, this is a tangent, at the point of contact between this liquid and the container glass, that is solid. So the solid surface, this is the solid surface. So here is solid surface, this is our liquid surface. So there is an angle between these two surfaces, more correctly angle between the solid surface and the tangent at which the liquid surface makes a contact with the solid surface. This angle is called angle of contact. So the angle which the tangent of the liquid surface at the point of contact, at this point, at the point of contact, makes with the solid surface inside the liquid, because it should be inside the liquid. So this solid surface which is inside the liquid, so this is the solid surface inside the liquid here. So angle between tangent to the liquid surface, this surface tangent is this, angle between tangent to the liquid surface at the point of contact, here is the point of contact, with the solid surface inside the liquid. This angle is called the angle of contact. This angle of contact can be acute or it can be obtuse. In this case, this angle here you see, check, suppose like water, this angle is less than 90 degree, so it is acute case. So in acute cases what happens is the addition force, the force of addition between this water molecule and the glass will be greater than the force between water molecule. That is why this glass can apply greater force on the water molecule than it comes to this side. But consider mercury, the molecules here inside these mercury molecules apply greater force of attraction between them compared to the force of attraction between the mercury molecule and the glass. So that's the result why this angle is here, that is an obtuse angle comes here. In this case we have an obtuse angle here. So here also angle of contact is defined as the angle between the tangent at the liquid surface, this liquid surface tangent at the point of contact inside the liquid. So this angle is obtuse in this case. So here cohesion is more than addition.